What's poppin', guys? Today we are going to review implicit differentiation. Implicit differentiation is where we are finding derivatives with multiple variables. You might remember this as the unit where you have to write dy dx after certain terms, so let's just go back through this. So if I have a simple quadratic function and I want to find dy dx, I just find the derivative because the y is already isolated. These were our easy derivative problems. These aren't too bad. But what happens if I write an equation like this, like 3x squared plus 2y equals 5? I could get the y by itself, but let's just say I wanted to find the derivative directly. So now we have an issue because we have that y. And remember that y is really the same thing as f of x. So that y is a function of x. It could be any function. So let me just write it as f of x, because I think it actually makes it a lot easier to see why implicit works the way that it does. I'll start by finding the derivative of 3x squared. That's just 6x, that's not too bad. But when I find the derivative of f of x, I want the derivative of f of x, f prime of x. I don't actually know what f of x is. It could be an exponential, it could be a log, it could be anything. So I'm just going to call it f prime of x. Now our goal is to find the derivative with respect to x, which is our f prime of x. So I'm going to try to get the f prime of x by itself here. So I'm just going to subtract the 6x over and divide by 2, and we find that f prime of x is negative 3x. So now as we proceed, we want to keep in mind that this entire time that f prime of x is really the same thing as dy dx. So I can write it as dy dx, and that's our negative 3x. So all along that process, the f prime of x's were really dy dx's. So I can replace the f prime of x's with dy dx. And swapping those out should look pretty familiar. You know, now it looks a little bit more like the problems that we did earlier this year. Let's try a more complicated one. Find dy dx for y squared plus y equals 3x plus 5x squared. So the first thing that I'm going to do here is I'm going to, again, replace the y's with f of x. It's easier to talk about implicit differentiation when you remember that the y's are their own functions, and those f of x's could be any function. Exponential, log, quadratic, it could literally be anything. So now we have this expression rewritten, and we can see that it's some function squared plus some function equals 3x plus 5x squared. So now we're going to start to differentiate. So we have to use chain rule. You got to bring that 2 down, leave the f of x the same, raise to the first power, and then multiply by the derivative of f prime of f of x, so whatever the derivative of that function is, plus the derivative of f of x, and then on the other side we just have our 3 plus 10x, which isn't too bad. At this stage, I would recommend that you pause and just double check that you're good with the left-hand side of the equation. So from here, we have our chain rule, and I'm actually going to replace the f of x now with a y, and the f prime of x with dy dx. So we have 2 times y to the first power, but we don't need to write that, dy dx plus dy dx equals our right-hand side. So I've just replaced the f of x with y and the f prime of x with dy dx. Now, all that substituting of f of x, we can just skip all that. If we just take a look at the very beginning of the problem, we had that y squared plus y. Well, the derivative of y squared is just 2y dy dx, and the derivative of y is just dy dx. So that's usually the jump that we made when we did these problems earlier this year. So you guys are welcome to just make that jump. But hopefully the f of x substitution kind of clarifies where that stuff comes from. So now I have to isolate dy dx because we are trying to solve for dy dx. Well, we have 2 dy dx's. So whenever you have multiple dy dx's, you have to either try to combine your like terms or factor. So we're going to factor out a dy dx here, leaving me with a 2y plus just 1. Make sure you remember that 1. And then we still have our right-hand side of the equation. So now to get dy dx by itself, I just have to divide both sides by 2y plus 1, and we have our final answer. It is a rational function with two variables.